Hey there, awesome physics students. Let's talk about resistance in electric circuits, specifically the resistance of wires or other objects that we're trying to pass electric current through. First of all, let's consider if we have a huge fat wire here and we're trying to pass some electric current down the length of it. Well, to do that, you're going to need a potential difference across the wire. You're going to need charge to flow from high potential to low potential on the other side. So if we want our current to flow this way, we're going to need some kind of electric field to get those charges to flow through the wire down there. And of course, we always define current in terms of positive charges, just like everything else in electricity. Of course, we know that it's really electrons that are flowing in the wire, and electrons are negative. However, we still define everything in terms of positive charges. If it makes you feel better, we imagine that the current flows in the same points in the same direction as the electric field. Now that's another thing. The electric field in this wire, which is a conductor, is not zero. But before I said the electric field inside a conductor must be zero. Well, yes, but that was under the assumption of electrostatics. That means charges were not moving. Here, this is electrodynamics. Charges are flowing through the wire. Charges are moving, and so we do have an electric field. And by the way, the charges that are flowing here, if we imagine them shoulder to shoulder like this, flowing down the wire, they don't all flow down the wire and then pop out the other end instantly. You probably heard that electric signals travel near the speed of light. That's true. The charges themselves do not travel near the speed of light, though. What does travel near the speed of light is the electric fields. Those are the things that are traveling near the speed of light. What we actually have is we have charges, and there's gobs of them, like Avogadro's number of charges in the wire, and they're all moving extremely slowly down the wire. But because you have so many of them, that gives you a noticeable current or a noticeable flow rate in the wire. Okay. If we have a fat wire like this, compared to a thin wire, let's imagine cutting this wire in half. So if we were to just consider the bottom half of this wire, these charges, if you imagine them standing shoulder to shoulder, you would get about twice the flow rate of charges for the whole wire than you would from just half of the wire. And so if this wire has a cross-sectional area of A, then the resistance will be smaller if it's bigger area. And specifically, if you double the area of the wire, the cross-sectional area, you're going to get half as much resistance. So the resistance of a wire is inversely proportional to the area of the wire. What about the length of the wire? Well, if you have a certain length of wire here, and it takes a potential difference delta V to get a certain amount of current to flow. If you double the length of the wire, so you have now two links, then it's going to take you delta V for this section to get that much current to flow, and delta V for this section to get that much current to flow. And so the total voltage difference is going to be 2 delta V from end to end. Because you have to have twice the potential difference to get the same amount of current to flow, that means the resistance has doubled. So in this case, this is telling us that resistance is directly proportional to the length, right? If you double the length, you double the resistance. Finally, there's a property of the material itself in here. So if we use copper for this wire, then it's going to have a lower resistance than if we use aluminum or iron or something like that. Copper's the best cost-effective conductive material that we have. Okay, so that is a property of the material itself. And this symbol here is rho, and that one is called, quantity is called the resistivity. Okay, and you can just look those values up in a table in a book somewhere. All right. Finally, let me just make a note about drawing these resistors in circuits. So we usually draw the wires as just lines, and then if we have a certain element in the circuit that is functioning as a resistor, we draw it as a zigzag line like this. We label it with the letter R for resistance. And we treat the wires themselves as if they had zero resistance. Now, they don't really have zero resistance. What we're really saying there is that the resistance of this object here, this circuit component, is so big compared to the resistance of the wire. Or in other words, the wire's resistance is so tiny that you could just, maybe it's 1,000 or 1,000,000 times smaller than this resistance. Then you just ignore the resistance of the wire. Okay, you're not saying it's literally zero. And as usual, we draw batteries as two wires like this. And the longer stem here is going to be the positive side and the shorter side is the negative side. Okay?